breakdowns. This is my own, my own little wording here with this stuff, okay? If you notice at the back of your notes packet, there is like a legit flow chart for every single test there is, okay? So you can look through all this, like this might make you feel better too on figuring out which one to use. And then this is my thought process. So I'm just kind of trying to give you all the tools so you can help figure it out, okay? So the first test we did was if you could find the sum. So like the pros are super easy only if you have the S sub n. Okay, if you have to come up with the formula for S sub n, it's just like a little annoying, takes a while. That's like number 3. Number 3, we had no option. That one's only doing this first test, okay? Tests, and then cons, yeah, again, finding the sum, super hard. Test 2, okay, is geometric series. This one is pretty easy for the most part because all you need is R. Sometimes it takes some work to get R, but the con of it, it has to be in a certain form. So if it's not in the form, you can't do it at all. Okay. Test 3, is nth term test, which is the best one in my opinion. Like I love this one, but it doesn't work out a lot. You just have to make sure it doesn't equal 0. But the big deal with this guy is that it only tests divergence, not convergence. So it doesn't even, it's only for divergence, which is sad, but it's fine. Okay, so here's number 4. Integral test. Okay, so I'm going to have to show you this proof because they started trickling these in to more AP tests. So I'm going to show it to you, and hopefully you can make sense of it. It's for integral test. I kind of avoid this one because you have to integrate. Literally, that's the only reason. But also it's very picky on when you can use it. So you can only use it if like the equation in your sigma is positive all the time. So I'll say I'll name it A. So you have to check it's positive. You have to check that it's continuous. Okay, so you can't have asymptotes and removables and all that junk. And then this is the worst one, decreasing. So you have to check it's decreasing the whole time, okay? So if the whole gist of it is if you integrate from, notice that here your sigma starting at 1, my integral starting at 1. If that was starting at 2, my integral would start at 2. Those have to match. It's saying if you integrate this function, you redefine it as f of x, and it's and you get infinity, then it diverges, the series does. And if it equals like a number, then it converges. Okay, so I wrote like a little note, like try this test if the function is not geometric and the nth term doesn't work. And I would add in, and it's easy to integrate. Or, actually I'm going to add this right now, or has weird functions in it. Like if it's got like natural log and stuff in the series, because usually series don't have weird functions in it. Okay, so I have to show you this proof, okay? Now, the proof is kind of like squeeze theorem, but it's not. So, like, you know how squeeze theorem, the numbers have to match on both sides? For this one, they don't have to match. They just have to converge on both sides. So, like, if your integral will be in the middle, okay, and then your series on the left side has to be less than or a number. It has to be a convergence. And then you have the integral in the middle, and then the other series has to be convergent. So if they're convergent on both sides, it forces the integral to be. And then they're divergent on both sides, it forces the integral to be. So I know that is kind of confusing. So that's just kind of, it uses Riemann sums to kind of reason to come up with this test. So, okay, notice first for both of these, they are, so notice they're both positive, like they're all above the x-axis, right? They are continuous. There's no like asymptotes or weird things. And they're all decreasing. This only works for that type of function. Okay. Now this is where it's kind of a weird thing here if you have your sigma notation. Okay. What they treat a of n as is this is your like height in your integral. Okay, so just think of that as that's like your f of x. Okay, that's your height. And what you do is you assume the width is 1. It's width, but it's invisible, right? Because you're not going to write a of n times 1. So they're using the idea that I can use an integral for this, thinking about how each of my terms are like my height, and my width is always 1. Because if you think about it, you're only plugging in like whole positive numbers into this. Like you're only plugging in 1, 2, 3, 4. If you think about it, your widths are always going to be 1. So like between each of your terms, like if you wrote them all out, each of your terms are going to be like one after the other. Like I'm going to get the first one, then I'm going to get the second one, which is just 1 over. So like what this looks like here on the graph is like, this is like your 1, like n equaling 1. This is your n equaling 2. This is your n equaling 3, dot, 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 until infinity. This then would be like your n, and then your end point would be n plus 1. And that's how it would be for both of these. So this would be 1, this would be 2, 3, dot, 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 n, dot, 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 n plus 1. Well, actually, that wouldn't be a dot. Hold on. Okay, so if you were to find an actual area under this curve, right, this picture would obviously be an overestimate, right? Okay, so if I were to find the area under this curve, okay, it would be from 1, because that's where I'm finding the area from. So I'm trying to find this, right? So I'm going to go from 1, and I'm assuming this is going on forever, but it's going to go until this last endpoint, right? So it's going to go until n plus 1. So this is like your full, like the full area is from 1 to wherever I need to stop finding the area of.
How do you know it's supposed to go to n plus 1?
It's the way the proof is set up. Okay, so you want to use n plus 1 for this because of the Riemann sum. So just hold on. Hold on. Yep. Okay, so this would be of whatever my function is, f of x dx, right? And this is going to be less than, right? Or equal to, I mean, that's not, it's probably just less than, but maybe it could be equal to, right? This Riemann sum, okay? So this would be sigma, okay? But if I'm doing my left values, okay, at n equals 1, okay, this is a left Riemann. Bless you. Okay, I'm using, right, this first n to get my height, right? This would be my a of n. Or it would be actually a sub 1, right? That would be how I get that first rectangle. And then my second rectangle, right, if I plug in 2, this would how I get my height. This would be a sub 2. AKA, these would all be f of 1. This would be f of 2, right? These are how am I generating my turns. This is how I'm getting my heights. This one would be a sub 3, okay? AKA f of 3. Now here's the deal. If I'm using Riemann sums to approximate it, and I'm using left Riemann sums, okay? Think of like your tables here. You're going to stop at a sub n if you're using left Riemann sums, right? Because that'll cover your whole area then. So this sigma is going to go up to n, and it's going to be a sub n, and then obviously the 1 is kind of invisible, but that's how you're finding those areas. Let's just go. It's kind of confusing, okay? So just hold on. So then, if I'm looking at the other one, I'm using right Riemann sums, okay? So this one is going to be an underestimate because it's below the actual. So if you're comparing your integrals, we'll put it here, your same integral, n plus 1 of f of x dx, is now going to be greater than or equal to a right Riemann sum. Okay. So, if I use my a sub n here, times like my invisible 1, if I'm using a right Riemann sum, the way I generate these terms for a right Riemann sum is starting at 2. Right, to get my height, I would use a sub 2 first. So my sigma is going to start at 2 because I'm using a right side. Yes?
I thought they have to match.
Hold on. We'll make a match. So hold on. So then here, if you kept going, getting, your rectangles, you do 3, right? You do n, and then your last one would be a of n plus 1 because you're using right Riemann sums. So this sigma is going to go to n plus 1. Okay? So now this part's maybe a little weird, but what I'm going to do is I'm going to add, to make these equal, because my sigmas don't match right now, right? I'm going to add this first guy in. I'm going to make it start at 1. So I'm going to add a sub 1 to both sides. Yes, we're trying to get them to the sigmas to match. That's the goal right now. Okay? So if I add them to both sides, my integral, it's just being added. Like I can't put it in the integral really. So it'd be n plus 1 f of x dx plus a sub 1, right? And then is greater than or equal to, excuse me. Now with this one, since I'm adding and we're dealing with a sigma notation, this is now exactly what I want. It's going to end up being, if I add an a sub 1 into it, this is now into n equals 1, so a sub n, and this is still going to n plus 1, but at least we're starting at n equals 1. Okay, so hold on. So, as n goes to infinity, if I were to combine these inequalities, okay, I have, so my least, or my smallest thing here, right, would be this guy. right? This guy would be my absolute smallest thing. So that would be 1 to n plus 1 f of x dx is less than or equal to this guy, my left Riemann sum, which is less than or equal to the integral from 1 to n plus 1 f of x dx plus a sub 1. So here's like the thing here. So we've got both of our series. So actually maybe I should put these in the same color, sorry. Here's my series, right? In the middle. Okay, here's my series in the middle. Okay. I made them the same, so actually I could make that blue too. Maybe I'm messing you up with the color, sorry. Right? This is actually, maybe I should change actually that. I can change that to infinity now. If I go n to infinity, okay? Those two sigma equations are the same. Okay? Because I made them such as n goes to infinity. Now this represents, right, my wait, did I mess this up? No, I didn't. No, my underestimate. This represents my overestimate, and you can see how you can figure out whether this converges, because if this is less than it, this was greater than it, as n goes to infinity, if you find the area of this and you get a number, and then you find the area of this and add in just one more number, it forces it to converge. And if these go both diverge, so say this goes to infinity, this goes to infinity, and then you add like a 3 or something, it forces the sigma to diverge. Yeah. I'm not, don't say it, sorry.
So, just to clarify, the only reason we added the a sub 1 was because it was n equals 2 and we wanted it to match.
Yes, exactly. Yes.
You didn't have any a sub 1, so you just had to.
You had to add it in, yes. Yes. I'll show you some multiple choice, because this is where I've seen it come in. I haven't seen you having to write out an FRQ, this proof at all, but I've been seeing it in multiple choice with different contexts.
So the top term doesn't have on that.
No, because you're going, I mean, the top, you're taking n to infinity. So like, even if this is a little bit more than infinity, it's still going to infinity. Same with this one. So. I feel like if we do, I have some on the warm-up tomorrow too, or on Monday. Okay. I'm only gonna do like, not a ton of these.
Well, there's 4, so.
We'll see. Okay. So, first one. Decide whether the integral test can be used. So the first thing you need to do is decide if it's positive all the time. So if you're plugging in, you're plugging 1 and anything later, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. N's greater than or equal to 1, right? Because the numbers you're plugging in are never negative. It's always positive numbers you're plugging in. So that checks. B, is it continuous? And you're like, why is there a denominator? So again, the denominator is what's going to mess that up. So if you set that equal to 0, I mean, you can kind of tell already that's going to be, it doesn't ever happen, so this is yes. There's not an asymptote, right? This is my least favorite. Decreasing. Yeah. see, I did in blue, yeah. Decreasing, yeah, like how do you decide if it's decreasing? Set your equation equal to f of x and change it to x's. Okay, because you're doing f of x, so you change it to x's and you get to do a derivative. This is why I love integral tests. You know? That's why I avoid this one like the plague. And quotient rule. It's like the trifecta. Loving my life.
Well,
Okay? It shouldn't be so dramatic. But anyway, so you do a first derivative, you have to figure out it's decreasing, so it's like, ugh. Denominator, don't have to worry about at least, but the numerator, I have to do algebra, which is fine. I'm having a positive attitude right now, okay? So, yeah. Set that equal to 0. Uh-oh, wait. 1? But it's 0 at 1. So wait. It would be 1 on. Because I can't do negative 1. Negative 1's dumb. Because it's n is never negative, right? So that one's not even here. But then here, if I do in the derivative, if I do anything after 1, it's negative, isn't it? Yeah. So it is. F prime of x is less than 0 for when n is greater than or equal to 1. Well, okay, when it equals 1, it's 0. But so maybe I'd get rid of the bar.
So what if it's not any of those three, you just can't do?
Then you can't just do it. Which is like a happy feeling in a way.
But then what do you do?
What?
What do you do?
Now we're going to do the test.
Well, no, I'm talking about like what if you
Oh, you have to do something else. You get to get your big eraser out.
force you to
Yeah. 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 Okay.
did you really have to do the derivative, or would you just look at it and be like,
Or you could, yes. But if it's on, okay, so guys, listen up. If you're on multiple choice, of course, like I wouldn't do it. But like a F or Q, yeah. Like pretty much everything. Like, yeah, you can be like, well, yeah, it's, you know, yeah, yep. Okay, so now I can do the actual work. Okay, so this is what you do. This guy, whatever that is where your integral starts, 1. Okay, so sometimes it's 2 or 3, okay? And we're going to go to infinity. And then we're going to do x over x squared plus 1 dx. And just like our improper integral stuff, okay, remember you have to do all your fancy things. Limit as not x, b. I usually use b for the upper bound. Goes to infinity. Remember? Throwback.
don't remember it at all?
Well, now we got to remember.
Hey, we have 7 minutes left.
Okay? I know. That's how you know it's a good one. So then, now you integrate it. Great time to be alive. Okay. What is this? Oh, duh, U sub. Right? Obviously.
Natural log of x squared is also
Oh, yeah. Do you remember parts? Parts is on there. Of course. Do you like integral test? Do I like integral test? No. Of course I don't. Look at this. You know, it's fine, but who cares about my opinion? No one cares. No one cares. No, I don't. Thank you, but, you know. Okay, so to keep my notation legit, okay. Okay, to keep my notation legit, I'm not actually putting bounds on this because otherwise I have to deal with that with my infinities and b's and junk. So this is almost like my side work here, because I'm gonna get this as, what is this, 1 over u du, right? So this is like my side work. So what is that? X squared plus 1. Technically plus c, right? Now the reason I'm doing this off to the side is, again, I don't want to deal with writing the limit over and over and adjusting my bounds. Because the second I use u sub, I have to adjust my bounds. So now I can actually put in my antiderivative. Yeah, like parts is a thing, u sub, any of those. I haven't seen completing the square. No, that's why I wrote it like this over here. Because then when I put it back in like normal x's, it's like I don't have to futz with it. So then now we do limit b goes to infinity, and we plug in the upper bound minus the lower bound. And then think. I didn't. That's why I put this off to the side. To keep my notation right. So you can almost think of all the pink as side work. And then I wrote in the antiderivative with like my x's and stuff, because then I didn't have to fuss with the bounds and the limits. So I did it like, the side work kind of. Okay. All right, so what does this equal?
I don't know.
Infinity. Diverges by integral test. Now we are.
So we don't need to do any of that, like setting things equal?
What do you mean? No, that's the proof of the integral test. So if the integral diverges, the series does.
You don't do that any greater than.
Nope.
That was just a big.
That was the proof for why it works.
Yeah, we would have trusted you with that.
No, but they're doing more stuff with it. That's math. College math, people. Okay. Really quick, because we're running out of time. Notice this. Okay. This one is increasing when x is greater than 5. So you can't use it. Oh, darn. Okay. Okay. I'm telling you it's positive. What is it? Continuous decreasing. Okay. If you do this one, hold on. Oh!
Faster, faster, faster.
Do you know how to antiderivative that?
Tangent, inverse tangent.
Inverse tangent. Good job. Oops.
Natural law. What are you, crazy?
I know. Ah!
Faster, faster.
Inverse tangent. Just hold on.
No. I'm not writing any of this down because I want to figure this out. We need a worksheet. We need a worksheet.
You just trusting me. Okay. Now, do you know what that is? As b goes to infinity.
Purchase a certain asset.
What's B? Isn't it
Infinity. No. Pi over 2. This is pi over 2. And then tangent of 1. Inverse tangent 1. Pi over 4.
Thank you.
Oh wait,
No, she did. I was just saying that.
Wait, there's one more. Oh, sure.
What?
I did. And I'm just saying that's an example.
When the review is actually
Why is there 12 questions?
Are you kidding me? We got through one today. They're all mostly
like I'm not gonna just do this on Sunday.
in the car sobbing as I'm trying to solve
Good thinking, Eli. At the table. Good thinking.
Please in the office, please. Coleman Keys, Gabriela Valente, Nathan Rudd Barantino, Cole Morris, Annalie Rivera, Grace Rosenfreder, Alyssa Brindowski, Andre Galvez, Blake Hoffmeister, and Maureen Torres. Attendance, please.